Today we have as our speaker Dr. Aravind Reddy. Aravind was a postdoc at the Broad Institute of MIT and Harvard, where he worked on computational biology. He graduated with a PhD in computer science from Northwestern University, where he was advised by Professor Konstantin Makarchev and Professor Aravind. Prior to this, he received a bachelor's from IIT Kanpur. His research interests lie in clustering graphical models and causal inference. Today he'll be talking about MAP inference of Ferromagnetic Potts models and non-symmetric determinantal point processes. With this, I hand it over.
Thank you, Srinivas. Good morning, everyone. Thank you for coming to my talk. So even if you don't know anything in the title, that's totally fine. I'll explain everything. And if you have any questions, please feel free to ask them during the talk. So today's talk will be based on two papers. So the first one was joint work with my advisor Aravind at Northwestern University and some collaborators at MIT. And the second paper was with collaborators from Adobe Research. So a brief outline for the talk. We'll give a brief introduction to probabilistic models. Then we'll go on to the part of the ferromagnetic Potts models. Then we'll go to the non-symmetric determinantal point processes. So this is a famous statistician called George Box. And this is all models are wrong, but some are useful. So today, the whole talk is about probabilistic models, and we'll be trying to model real-world phenomena or real-world data. So it's the case that the models will never applications. A very brief timeline of scientific modeling. So before the 17th century, most of the models were deterministic models. So this is Principia Mathematica, in which Newton gave three laws of motion, and they're all deterministic models. And post 17th century, a lot of the models we developed are probabilistic and statistical models. Here you can see a lot of names which are familiar to you, like Bernoulli, Bayes, Laplace, Kolmogorov, and whatnot. So today's talk will be about a particular aspect of probabilistic models called MAP inference. So this is just one aspect of probabilistic models. So there are a lot of other aspects which are important. So for instance, you want to actually learn these models before you do MAP inference. So that's like one thing, learning undirected models. But today's talk will only be focusing on this inference part. So this is from a book called Probabilistic Graphical Models, which came out in 2009 by Daphne Koller and Neil Friedman. So this is by now basically like a very standard textbook for teaching courses on probabilistic graphical models. And this particular textbook, I think it has more than 10,000 citations by now. So what is the maximum-a-posteriori inference problem? So here we want to find the most likely assignment for the variables for any learned probabilistic models. So the reason why it's called posterior inference is because you want to first learn the given model, and after that you want to find the most likely assignment. And typically these are discrete combinatorial optimization problems, and as is often the case, most of these are NP hard, and therefore if you want to do this quickly, you will usually resort to approximate inference algorithms. A brief overview of our Potts model's results. So in this Potts model, we'll be using a graph to represent the probability distribution. And for the Potts models, we go beyond worst case analysis to show why LP relaxations give excellent performance in practice. So this particular paper, it appeared in AISTATS 2021. And for the determinantal point process results, so determinantal point processes, they use a matrix to represent the distribution. And for DPPs, we provide the first one-pass algorithms. And this paper appeared in ICML 2022. Yes. The parameters are represented, yeah. So for water graph, so if you want to look at any particular binary distribution over n variables, to represent any arbitrary binary distribution over n variables, you'll need 2 to the n minus 1 parameters. Basically, for every possible 0, 1 string, you have some probability value, and the only constraint is that all of them need to sum to 1. But this is infeasible for, like, this is too big if you want to actually use them for any realistic applications. Like, even if you only have like 1,000 variables, that's already infeasible. So instead, what people do is they use graphs to model these dependencies, and that can significantly reduce your model size and can give you useful things to do. So typically, when we use graphical models, like directed graphical models, these are called as Bayesian networks. For example, one property for Bayesian networks is if in the corresponding graph, if there is no path between two nodes, then in the distribution corresponding to those nodes, the variables are conditionally independent given any set of other nodes. So Bayesian networks were invented by Judea Pearl in the 80s, and he also developed a lot of inference algorithms for them. And he received the Turing Award in 2011 for his work on graphical models and also for his work on causal inference. So our talk today, we'll be discussing undirected graphical models. So these are also known as Markov random fields. The graph corresponding to these distributions is an undirected graph. So what is this ferromagnetic Potts model? So here we have an undirected graph in which for every node in the graph, the corresponding variable, it can take values from 1 to k, where k is greater than or equal to 3. And the probability of any particular labeling from 1 to k to here, for any given model parameters theta, the probability of any particular model, like probability of x theta, is proportional to exponent of minus q of x theta, where this q is also known as the interaction energy. So the reason why we have all this ferromagnetic energy and these things is because these models were initially developed for magnetism, like ferromagnetism. And if you are familiar with the Ising model, it is basically just this model is a generalization of the Ising model. So in the Ising model, you are allowed only binary states, +1, -1, or 0, 1, whereas here you're allowed to go up to k states. So the particular this energy function
probably the interesting aspect is dimension of theta has to be. So I'm assuming that theta itself is a vector.
Yes, we'll discuss what this theta is here. So here, this theta, it consists of two terms. So one is there is a node term, and then there is a edge term. So we are only considering like unary and binary potentials, but in general, this theta can go up to arbitrary number of like if you want some k. But as you are increasing like triplets, quartets, and so on, the model just gets like bigger and bigger, and it becomes harder to both learn and also to do inference. So this particular model, we'll only be looking at unary function and this binary function. So basically, like we'll discuss like what these things are, but here in some sense, the intuition is that if you look at these ferromagnetic models, then these single node terms, they are representing the like prior probabilities. So somehow you learn from the data that individually each node, it has some preference for any particular label from 1 to k. And these edge terms, they impose some interaction between the nodes. So I'll give a particular example, but in the graph, these are typically the neighboring nodes. So they impose some sort of smoothing constraint out. It encourages clusters to form. And this Z is also called it's a partition. It's called the partition function, and it's basically the normalization constant for this distribution. And even computing Z like this is a different problem. Like we'll not really care much about Z, because the problem which we care about is finding the most likely value of X. So since this is common for all possible values of X, we don't really care about this Z, but that is also a very well studied problem, computing this partition function. We will assume some properties, we'll discuss. So there are a lot of applications for these parts models. So in particular, this talk will be looking at a computer vision application. So computer vision is one of them, and it's also used in social sciences, finance and market modeling. And there are a lot of applications in biology as well. So protein folding and other structured prediction problems, genetic and evolutionary models, ecosystems and species diversity, and cellular systems. So the particular computer vision application which we'll be looking at is called stereo vision. So in stereo vision, you are given two images, two 2D images. So these things you can think of them as like if you use a camera, like if you use a phone with two cameras, then one image is the one which is captured by one camera, and the other one is the image captured by the other camera. And these two images are very similar to each other, but they are slightly different. And using these differences, you can compute something which is called as a disparity map. So for every pixel, you want to find how much is it different compared to the other pixel, and that information, you can use it to compute a 3D map. So if a pixel is like, if some object is closer to your camera, then the two images will be differing more. And if it's farther, then they'll be similar to each other. And to do this, we'll be using a particular graph, which is this grid graph. And so for every pixel in this image, we'll have one corresponding node, and then every adjacent pixel, there is an edge. And for every edge, there is a non-negative edge weight, which will be representing by this WUV. And for every vertex, we will have an associated cost, CU of I, where I is a value between 1 to k. So for every assignment from 1 to k for this particular cost, like pixel, there is some associated cost. And our goal is to label these vertices to minimize the potential, because if you remember from the earlier probability distribution, the probability is proportional to exponent of minus of this energy. So if you want to maximize the probability, then you want to minimize this potential function. So basically now we'll just move on to this particular optimization problem, where given this weights and costs, there is some corresponding graph optimization problem, which I'll discuss later. Yeah.
Are they non-negative or they be negative also? The weights and the C.
So the WUVs are all non-negative. And for CU of I, it doesn't really matter. So even if you have a negative cost, you can basically just add a constant term to everything and make it positive. And that doesn't actually change your optimization problem. So we can assume that CUI is non-negative also, but it doesn't really matter. For WUV, you definitely need it to be non-negative, because if it's negative, then your optimization problem, we cannot use the particular algorithms which we will discuss. It turns out for that particular optimization problem, so the algorithms which we have are two approximation algorithms. And if you directly use those algorithms, and let's say this is the exact solution G. So basically what this exact solution is saying is that, like, once you have those assigned like 1 to k values, then you're representing them here as like grayscale images. So that gives you this corresponding image. And let's say this is the optimal solution for your optimization problem. Then a possible two approximation can be the solution. And this solution, if you look at the Hamming error, it can be greater than 99%. So although this cost is only a two approximation, if we care about, so what we actually care about ultimately is the Hamming error in some sense. And we are only using this optimization problem as a proxy to get there. And it turns out that this can be pretty bad. But in practice, the algorithms which people use in practice, even though you're only trying to approximate the objective function, actually the Hamming error is also very low. The Hamming error is less than 1%. Or basically even the actual optimization problem you solve, the cost function is not like a 2 approximation, but it is also like closer to 1 for the algorithm outputs. So there is a question here as to why is this the case? Like even though the approximation guarantee you get from the algorithm is a 2 approximation, it turns out that in practice you are getting much better guarantees.
So what are you trying to optimize?
A particular cost function like this Q of G, which I said, I'll describe the optimization problem. But when we are trying to optimize that cost function, that's only a proxy, because what we ultimately want to recover is this mapping. A bird's eye view of the paper. So in prior works by my co-authors, what they showed was that I will discuss those results first. So in prior work, what my co-author showed was that if you assume that the underlying theta that satisfies a particular condition called stability, then you can exactly recover the optimal solution. And what we showed was that even if it's the underlying cost function is not stable, but if it is close to stable, then you can still approximately recover the optimal solution. And we also showed that real world instances from computer vision, they can be modeled as corruptions of these stable instances with some noise. And we showed some experiments to back them up. This is only an overview. I'll go into the details. So this particular optimization problem in the TCS literature, it's called as a uniform metric labeling, and it was introduced by Kleinberg and Tardos, I think in a Fox 99 paper. And independently, it was also introduced by Boyko, Wexler, and Zabi in a computer vision ICCV paper. And here we have a graph with vertices V and edges E. I mean, here the example which we are looking at is a grid graph, but the actual optimization problem, it can be any graph. And we have these non-negative edge weights, and then we have these costs. So for every pair of vertex and possible label, you have some cost function. And this is the solution which you want to output. So this G is a mapping from this vertices to any possible label from 1 to K. So one label for every vertex. And this is the optimization problem which you want to solve. So there are two terms here. So first you have this node term. So you're just summing over all the nodes, the cost of U with the assigned label G of U. This is the node term. And then the second term is just a cut function. So you're looking at all the edges and you're checking if it is cut or not. So if both the vertices and the edge are assigned the same label, then it's not a cut edge, whereas if it is assigned different labels, it's cut. So you're just looking at the cut function. And so basically, if you don't have this this particular term, if you only are looking at the cut function, and also if you are restricting it instead of having access to K labels, but like just 2 labels, then that is basically the minimum ST cut problem. And even if you don't have this node cost function, so there is some additional vertex. So there is one vertex, the source vertex S, which you are assigning like, yeah. So it's basically ST cut, like the algorithms are same, flow algorithms they work. And good question, but yes. And for K labels, it's called minimum multi-way cut problem. It's a generalization of minimum ST cut, where you have 2 nodes S and T, whereas there you have K terminals T1, T2 to Tk, and this is closely related to that problem. So this problem is an NP-hard problem. There are approximation algorithms for this problem. So you have these linear programming based algorithms, which were introduced by the Kleinberg-Tardos paper, and also they were later improved. I think this particular Chekuri paper, I think it also appeared in SODA 2001. And the Boyko, Wexler, Zabi paper, they gave combinatorial algorithms, which are basically like max flow type algorithms. And both these type of algorithms give 2 approximations to solve this problem. And we know that assuming the unique gains conjecture, the best you can do is a 2 minus 2 over k factor optimal algorithm approximation. So unique gains conjecture is a pretty common assumption when you want to prove hardness of approximation. And in most cases, you care about the case where the k is like a somewhat big number. Like, for example, that computer vision applications, k is like 300. So essentially, the worst case analysis for this problem is settled. So for large k, you're showing that you cannot do better than 2 approximation, and you already have algorithms which are giving you 2 approximation. So the connection there is that if you don't have so this is generalization of multi-vector. It's a harder problem than multi-vector. So in multi-vector, you only have these cut function. You don't have these node labeling term, right? So if you don't have this, it's a strictly harder problem than multi-vector. Yeah. So for the worst case analysis, this problem is a settled problem. So it is exactly the same. There's no like reduction. So basically, the probability distribution, we had that for every labeling. It was proportional to the exponent of minus of Q of G, where that is an energy term. So if you want to maximize over all labelings G, this exponent of minus Q of G, that is the same as maximizing over all labelings minus of Q of this X G. And if you want to maximize this minus, then it's just like minimizing Q. So this exactly the same problem.
Problem is that you given a theta
Yes.
and you want to find the assignment at maximization. But in the image, the vision setting, what you actually have is a sample from that. So it's not a inference problem per se.
So you're already learning this model. So we are only looking at the inference part, but the actual model, you are learning it from prior data using other like algorithms.
So the thetas are given to you.
Yes. Yeah. So the thetas are not like given to you as in like, it's not already decided, but you learn that theta. And once you learn that theta, now you just treat it as something that's given to you.
So it's like saying that you have this parametric family or distribution, which is the most likely draw.
Yes. Yeah.
Most likely quantified as well.
Yes. So in some sense, that is giving you the probability distribution. But if a practitioner comes and asks you like, give me something which I can act upon, then that is the answer which you want to give, the most likely assignment.
I sample like in the other sort of counting complexity world, these two other things.
They are related. So these are called Markov random fields. So they are actually closely related to Markov chains, and the sampling problems you do like using Markov chains, and there are other techniques called Gibbs sampling and other things. So that's yeah, they're well studied. Yeah, in that big box which I showed earlier, like sampling was also like one part. But we care about this particular problem. Yeah. So we want to go beyond worst case analysis. And so, for example, one way you could go about is if you're assuming that the underlying graph is having some special structure like a tree, then you know that you can solve it exactly. Although this is a nice result, it's not applicable in practice because if you saw that grid graph, it has cycles. So this is not applicable. So this area of beyond worst case analysis in the recent couple of years in the TCS community, it has exploded a lot. And this book, Beyond Worst Case Analysis of Algorithms, it came out in maybe 2022 or 21 January, I don't remember. So it's a book, so this was edited by Tim Roughgarden, but like all of the chapters were written by individual researchers in this area. And so today we are discussing only this stable instances for this particular graph optimization problem, but basically this concept of trying to provide better guarantees for your approximation algorithms under some assumptions on the data is a very general thing. And a lot of other models have also been studied, like for tensor decompositions and in other clustering, like other graph problems like clustering and other cut problems and things like that. So it turns out that there is a nice property for the real world instances, which is that they are stable to perturbations. So what is that? So if you look at the problem instance, you have basically that costs, the node costs and edge weights. And if you solve exactly for that one instance, let's say this is the original instance, original solution. And if you take those weights and even if you perturb them to some extent, basically there you're looking at like a 2, you're allowed to multiply everything by a factor of 2. Then even then, if you solve, if you give the exact solution for that, they're very similar to each other. So this is like a nice property. So it's basically restricting the class of instances which you care about. So now you can hope to give guarantees which is better than the worst case. So the question is, can we leverage this structure to give better guarantees? So this notion of stability was introduced by Bilou and Lenial in ITCS 2010. And here for any optimization problem, we are defining a beta gamma perturbation of the problem, where beta and gamma are two parameters which are greater than or equal to 1, where for every parameter in that optimization problem, you're allowed to either decrease it to a factor of at most 1 over beta, or you can increase to allow up to a parameter like gamma times WUV. And any given problem instance is said to be beta gamma stable if the exact solution for that optimization problem is unique, and it also remains as the unique optimal solution for any beta gamma perturbations. So in some sense, if you think of the parameters as being in some high dimensional space, then you're looking at a ball around that region, and you want the solution to be the same in that entire ball. Any questions here? It has to remain unique. Yeah, this is required for some guarantees. Like basically, the particular problem which we care about, there's this linear programming based thing, and if you have two solutions, then the entire like convex combination of those things, it can lead, so that leads into issues. So this uniqueness is important. You can test it. So we will discuss that. You can test it. I mean, even testing that is also like another NP-hard problem, because first of all, to test that, you need to actually exactly solve the thing. And then, so a nice property is that although I said that this, although the actual condition is that it needs to be same for any beta gamma perturbation, you only need to check for one particular adversarial perturbation. Once you solve the problem, you get like the solution, and given that solution, you will essentially like perturb these other weights to make the solution as bad as possible compared to other ways. So you just need to solve this one thing, and once you solve it, there is one other optimization problem which you solve, and then that just gives you a guarantee that everything which is possible, it has the same thing. So it's a quite nice characterization. Yes. We are perturbing the constraint parameters, the edge weights and the node costs. Yeah. So the particular linear program is like the one which was later by Chekuri, Khanna, Naur, and Zosin. Is this linear program? Like it's a sort of simple linear program. So basically, you have for every node and a possible label x, like I, you have this term xui. And you have this constraint that once you solve for every label, for every vertex, like if you sum over all the labels, then this has to be equal to 1. And then you also have these for every edge UV, you have a variable for every possible pair of labels, XUV, IJ. And So if you saw like this earth mover distance or things like that before, this is like essentially the same thing. And if you restrict this to be exactly 0, 1, then this gives you the exact optimization problem. Basically, like for every vertex, there is only one label which has 1 and everything else is 0. So whatever is 1, that is your corresponding label. And basically, if you just relax these things to be between 0 and 1, instead of being exactly 0, 1, you get a linear program. But it's not really crucial what this linear program is, because we'll focus on some other aspect. Okay. In some sense, this is like a simplified version of this. So you can just think of this as some linear program where you have some optimization problem, which is represented as this inner product of theta and x. So this theta is basically just this long vector corresponding, which has all that cu of i's and also all this wuv's encoded in this thing. And this x is just one big stack vector for everything from the earlier like nk plus, that earlier thing. And with the constraint that this x belongs to some LG, which is some polytope. Yeah, this theta is edge weights and no label cost. And this LG is called a local polytope of G. And this is also like very well studied for even other problems. So what we show is that if you assume that the underlying theta, it satisfies something which we'll call close to stable. So we described what was a stable instance, which is that if you perturb, then in the whole thing, it has to be the same, the exact solution. But we'll relax that and show that, so the earlier results, they showed that if the thing was exactly stable, then you can exactly solve the linear program. But if you remember from our earlier discussion of that instance, if you actually care about real world instances, then you don't get the exact solution by solving the linear program, but you get like this 1% error. So that is what we want to achieve. So here, for every theta, which is basically this node cost and edge weights, we are defining this distance function p theta hat theta bar, which is supremum over all x in that polytope, the objective function. So this inner product of theta hat and x is just the objective function. So you're looking at all possible x and you're seeing how much the objective function can differ. So this is some notion of distance between these two instances.
Is there a difference between L star G here and LG?
Yes.
Because you're changing W itself. The polytope is defined using W.
The polytope is defined using G. So W's are just parameters. They are just part of this theta. Correct. So if you go back to these constraints, then in these constraints, nowhere do you have anything to do with W's or U's. This is just like for vertices and edges. So this is the same polytope.
It's like the outer cone for the vertex. So so every sort of optimal will be at a vertex, and somehow this distance is capturing like some distance between these outer cones.
Yes, but they might not be the same vertex, right? So that's why overall vertices you're looking.
L star G is the same as it.
Essentially the same. So basically this thing, you can convert it into some other optimization problem, which is, so you can, instead of these constraints, you have some metric constraint, which is like another linear program. And you instead care about like the polytope corresponding to that. That's why we use L star, but these are like more or less technical details, but you can basically think of it as just being LG. Yeah. So the theorem, which the main theorem of the paper is that if you look at any observed instance, G theta hat, and let X star and X be the optimal and the LP solutions. So optimal solution is if you are able to solve it exactly, what is the solution you get, and X is the LP solution, then this is essentially the parameter you care about, this Hamming distance between X and X star. And we can, and also let X bar be the solution of a, okay, I'll not describe what is expansion stable instances, but it's basically some stable instance. So if you look at any other stable instance, theta bar, then this Hamming error is at most this distance d between this theta hat and theta bar with this psi, where psi is just some. So the psi is an additive stability parameter. Like we had both these edge weights and node costs. So you're allowed to multiply these edge weights, but for the node cost, you are only allowed to add. So that's some technical detail. Plus this Hamming error between X star and X bar. So here, since this theta bar is a stable instance, you can exactly solve it. So this X bar is basically like is also the same as X bar star in some sense. So what you're saying is, if you have this given instance G, and suppose there is some other instance theta bar, which is like close to this instance, then essentially you can give some bound on the Hamming error for the observed instance with the distance between these two instances. So this theorem by itself, it doesn't like give you any actionable guarantees. For it to make sense, what you need to show is that for real world instances, you can actually compute like the stable instances close to the observed instances. Okay. And so that's why you have this problem, which is like, okay, how do you actually find these nearby stable instances? And turns out that even finding this nearby stable instances, you can basically frame it as a convex optimization problem, where it's not really important how you can solve it, but basically you can write a convex optimization problem, and then you can solve it using this LP solver called Gurobi, which is pretty common, and it takes some time, but essentially then it gives you. So we saw that for some observed instances, you only need to change like small number of node costs and weights, and that already gives you like a stable instance. And the theorem bound, the right hand side of that theorem, which we got, like it gives these like Hamming errors 40, like basically 0.48, and the Sukuvan cones are like two different images. And the observed error is actually much lower, 0.27%. But the thing is that we were the first to even give a non-trivial bound, theoretical bound. So showing something which is even less than 100% is still a very good thing for you, because earlier there was nothing. Okay. So that's it for this part. And future directions, there are similar problems where instead of analyzing them for linear programs, you can analyze for semi-definite programs. So the earlier problem that was like related to minimum multi-way cut, but I think someone asked this question, what happens if WUV can be allowed to be negative, and that you need semi-definite programs, and I think they correspond to like max cut instances. And also like other problems like clustering and maximum independent set. So for basically all these problems in that book which I described, they have in like prior results on stable instances. So you can try to show them for nearby stable instances. And these are also very related to stochastic block models. So some work which you can do. And so one interesting area is, so the whole thing which we did earlier was that, okay, somebody gave you some LP based algorithm or a flow based algorithm, and now you want to give guarantees for those algorithms. But more generally, if you assume that the underlying instance is already stable, you can try to develop new algorithms which are maybe not even related to those LPs or the prior flow-based algorithms. So this is another area. And to summarize, what we showed is that stability is a useful model for studying combinatorial optimization problems. And for certain instances, real-world instances can be modeled as stable instances with some corrections or noise. And this explains the excellent performance of linear program relaxations in practice. So this ends the first part on the ferromagnetic Potts models. If you have any questions, feel free to ask. So DPPs, for any given ground set of items, like from 1 to n, you want to give a probability distribution on all possible subsets of that item. And that is characterized by some kernel matrix L, which is an n cross n matrix, such that the probability of sampling any particular subset S is proportional to the determinant of L subset S, where this L sub S is the principal submatrix in that L matrix corresponding to the particular rows and columns in that S. So for example, the probability of sampling the set with just the first element is just the first L11 thing. And the probability of sampling the subset 1, 2 is the determinant of this first submatrix with the first row, first column, second column, and so on. In particular, it turns out that for this probability distribution, the partition function, which is a normalizing constant, is very easy to compute. It's just this determinant of L plus this indicator identity matrix. So here the probability is exactly equal to determinant of LS by determinant of L plus IN. But for the map inference problem, we still don't care about this, but it's just a nice thing to know. Okay, so for the matrix L to represent a valid probability distribution, we need that for all possible subsets S, the determinant LS, it needs to be non-negative. And the matrices which satisfy this property are known as P0 matrices. And it turns out that if you assume that the underlying matrix L is a symmetric matrix, then this P0 matrices, basically the determinant of LS being non-negative, is equivalent to the condition that L is a positive semi-definite, which is that if you take any X in Rn, then X transpose Lx is non-negative. Therefore, all symmetric matrices which correspond to valid DPP distributions are positive semi-definite. But it turns out that there are P0 matrices which are not necessarily symmetric. So this P0 is a condition that the determinant of every possible principal submatrix is non-negative. So if you look at this 2 by 2 matrix, this is a non-symmetric matrix, but the determinant of every possible principal submatrix is still non-negative. So these DPP distributions, they are very useful in any item subset recommendation problems. So for example, video recommender systems like YouTube and Netflix. And here the subsets are, you can model the set of videos which a user watches in a particular session, or like in a one particular consecutive viewing session, what are the subset of videos which they watch. And you also can think of e-commerce recommender systems like Amazon and eBay. And here the subset is like a basket of goods which a person buys. So you can think of all the Lord of the Rings and Hobbit and then be bought together. So it turns out that in all these video recommender system and also e-commerce applications, the number of the size of the ground set can be extremely large. So for example, in YouTube, I think I read somewhere that you have more than 14 billion videos on YouTube. So if you want a matrix that's already like 10 to the 10 times 10 to the 10 size matrix, which is extremely large, And even for Amazon, I think there was some statistics saying that they had like 400 million items or whatever. So if you want to use a direct n-cross n kernel, then it is often impractical. You just cannot use it for space constraints. So instead, what people did is they used this simplified version for L, which is a low rank symmetric matrix. So here you are imposing some rank constraint, and essentially this L, you can then represent it as a much smaller matrix, which is a D cross N matrix. So you have D rows and N columns. So for every item, there is a column of size D. And actually, it turns out that this is more or less sufficient, because although if you allow for this entire n cross n, then you are allowing interactions between all sets of items. But actually, when this matrix, when you learn it, the underlying items which you see, they are always in small subsets. Like if you have some user buying items, they'll never buy like 100 million items at once, right? So maybe at most size 20 or 30 or whatever is sufficient. So that is enough. And that is much smaller. DPPs have traditionally been used to encourage diversity in recommender systems, because essentially this problem, in some sense, if you want to pick key items, and if you think of them as being like points in RD here, like n items in RD, then maximizing that determinant is the same as, so that determinant is equal to the volume of the parallelepiped, which is spanned by the k items which you select. So yeah.
Please don't have it. Which set to identify.
No, it doesn't matter. So you have the probability, it doesn't matter, like. So for identifying the number of bits you would need is log n, but here this is a latent representation with, so for example, like if you restrict it to be like only on a 2D plane, even then you can, like, if you have n points and then you want to maximize the volume, but basically in 2D plane, you cannot have more than 2 items, because that will basically just give you 0. The volume of that matrix will be 0, but it up to k items is enough. So if you only need up to 10 items and your latent dimension is like 30, that's fine with you. DPPs have traditionally been used to encourage diversity in recommender systems. Like if you have somebody who's watching YouTube videos, then you don't want to suggest the same thing again and again, then they'll get bored and they'll leave. So instead you want to show some other things, and it's like some nice mathematical model to encourage that. But it turns out that symmetric DPPs can only capture repulsive interactions. So if you assume that L is symmetric, you can only capture repulsive interactions. Whereas so you only want to select some size k subsets where k is less than d.
If it's, let's say I have a rank D matrix, L has this rank D decomposition.
Yeah.
You're saying that the determinant of submatrices of size above
Less than d.
Above D will be 0, or will
Yeah. Above d, I think it will be 0. Yes. So basically, I think the matrix So if you take the case of like, let's say everything is in 2 dimensions, and or forget that, like everything is in 1 dimension. Yes.
Wait, I'm just.
So the
wondering,
principal submatrix
Yes.
which you get for
let's say a D+1.
yes, I don't remember exactly why that is.
So you are not in detail. You're still looking.
I mean, it's essentially it's rank T, right? So it's essentially T dimension.
D in R in.
I mean, after applying appropriate rotation, we can assume it's in D dimension. So the rank is D, so it's a D dimension space. So you can essentially assume it's a D dimension space.
I believe you.
So the volume of
You have n points, but for every point,
You are looking at, let's say D+1 plus D plus, maybe, yeah, being unnecessarily pedantic. I believe you will be,
so the rank you have n.
if I look at the full columns, you give me D+1 complete columns in Rn,
Mhm.
they are indeed lying on a D-dimensional space, agreed. But if I look at a submatrix, we are only looking at like D+1 dimensional vectors. And
Correct.
okay, I see.
No, so you're measuring volume in D plus one dimension,
I see.
but it's in a D dimension.
I see. Okay. You're not measuring volume in R, you're measuring it in
RT. Yes, yes. So this DPPs in machine learning, the discrete DPPs, symmetric ones, they were introduced in 2010 and work up to 2017 operated under the constraint that L needs to be symmetric. But after that, there was this notion of non-symmetric DPPs. If you take any matrix L, you can uniquely write it as a sum of a symmetric and a skew symmetric matrix. This is L plus L transpose divided by 2 and L minus L transpose divided by 2. And if you let go of this symmetric constraint, this skew symmetric component, it also allows you to model attractive interactions. So for example, if you're looking at this e-commerce applications, then if you buy a printer, you might want to increase the probability of buying a inkjet or something. Or if you're buying a pencil, then you want to maybe buy an eraser or a modem and a router and things like that. And 2021, they introduced a low rank NDPP decomposition. So essentially for the symmetric part, it's the same as before, V transpose V, but this skew symmetric part is written as this B transpose CB, where so L is the same, N cross N, and B is also the same as earlier, like D cross N. And this B is also similar to V. So for every item, you have like a D-dimensional vector. But in addition to that, there is a D cross D matrix C, which is a skew symmetric matrix. So that gives you these attractive interactions. So this is not like super important for our talk. You just, so what we do is, let's see here. Okay, so what we do is we provide the first one-pass algorithms for solving the MAP inference on this non-symmetric DPPs. So we give one algorithm which we call as partition greedy, which has some competitive ratio bound. And then we also have these online algorithms, and we also show some hard instance for these online algorithms. And so streaming algorithms are models. So streaming model is a model for algorithm for solving if the problem instance has a massive size, which can be larger than the physical memory. And here the things which you care about are memory usage and competitive ratio at the end of the stream. In our particular DPP case, what we have is after you've learned your model, they correspond to these 2D length vectors. So Vi is a D-dimensional vector, and this Pi is also a D-dimensional vector. And you store your data in this form. So you have these endpoints in some sense. So these are 2D dimensional vectors. And now you are allowed to go over the entire stream, and you want to pick the subset K, which is maximizing your objective function. And generally in streaming algorithms, multiple passes are potentially allowed, but the algorithms which we provide are only one pass algorithms. In online algorithms, they are slightly different. So here you're allowed to see the data only once. And the things which you care about are a bit different. So here you care about the update time and the commutative ratio at every time step. Instead of like the streaming setting, you only care at the end of the stream. So here you need to maintain a valid solution at every time step. And here only single passes allowed. So in our problem setup, you see the stream of vi, bi until vn, vn. At every time step t, you want to output a subset S to maximize that objective function f of s, which is this determinant Vs transpose Vs plus Vs transpose Cvs. So this actually corresponds to that L subset S, the principal submatrix. And since the probability of S is proportional to f of s, according to NDPP distribution, this is the map inference. This particular optimization problem is the same as the map inference problem for that model. Which one? So if you remember earlier, we had that that matrix L, you wrote it as V transpose V, right? So this V is just you have for every, you have n columns. Every column has at most dimension V. So instead of storing that matrix as like one block, you're just allowed to store each point, the d-dimensional point. So these VIs have that. It's like d-dimension in dimension. And similarly, you have these B's also in that. And this C which is there is like a D cross D matrix, and D which we assume is much smaller than N. So you're allowed to just store this D cross D matrix in memory. So then this entire optimization problem you can like. So we provide streaming and online algorithms, and we show that they perform comparably or even better than the offline greedy algorithm while using substantially lower memory. And for the online setting, we also show a hard instance. So we'll briefly go over this algorithm. So we have this algorithm which we call streaming partition greedy. And this is very similar to, this is a generalization of the greedy algorithm. So in the greedy algorithm, what you have is you have this n items, and you're allowed k passes. So what you do is you go over all the set of items, and you first pick the item which maximizes the volume for just that. So essentially in that L matrix, you're going over all the diagonal elements, and you're picking the element with the highest size or like maximum value, and you're adding that to your like subset in your algorithm, and then you're adding the second one condition on the first. So then you're allowing only let's say you select item 5, then you're only looking at 5,1, 5,2 until 5,n, and you're maximizing all that. So you go over all the n things k times, and you get your solution. That's a greedy algorithm. Here, what we do is we partition the n items into k buckets. So this is a bucket of size n over k, and then you have from n over k plus 1 to 2n over k, and so on. And now we select the first item among only this n over k items. And then the second item is conditioned on this first n over k, the second item, and so on. So in one pass, you can output a solution of size k. That is this algorithm. And you can show a guarantee for this. So you can show an approximation bound. So here, this approximation bound, they usually involve this log determinant terms, because that determinant, so if you want to maximize the log of the determinant, then that's some submodular function in some sense. Here, this is not exactly submodular, but close to submodular. Then you can use guarantees for submodular function. You have this 1 minus 1 over e guarantee, and they sort of translate to guarantees here. And what here we show that if you assume that the underlying stream is arriving in a random order, then you can show an approximation bound for this algorithm. And you actually need this random order arrival, because if you don't assume this random order and adversary is allowed, then you can have all the best k items at the very end of the stream. So then, irrespective of whatever algorithm you do, you cannot, like in one pass, achieve any meaningful approximation. And similarly, we have this algorithm called the online greedy algorithm. So here, what you do is initially you form a subset K by looking at the first K items. And then after that, whenever you see a new item, you look at all the items which you have and you take out one and you add that other item and you check if that is increasing your optimization, like objective value. And if it does, you increase it. So this is like a simple algorithm and it's also been used in other settings. We just applied it to this particular like non-symmetric DPP case. Then you also have a more complex algorithm, which is called this local search with stash algorithm. So here, what you're doing is instead of just looking at one item, you have some buffer of items, and whenever you get a new item, you add it to that buffer, and then you perform a local search with up to some number of elements. So here we are only like doing like here you are allowing only one-step local search, but then there's a more general two-step local search version. So the reason why you are like taking that stash is like if there is some item which if there is no stash, you'll just kick it out because you don't have memory. And it could be the case that like that item has some corresponding other item which will increase the value a lot, but you've not seen that till now. So basically these things, if you think about this problem more, they sort of become intuitive. It's not like super important to go to details. The paper is there, so you can go and read. And this two neighbors search is like a more complex one. You're allowing up to 2 items. So you still maintain the stash, but you're allowed to change 2 at a time. Then we have some experiments on these data sets. So this Amazon apparel is a public data set which was released by Amazon for a bunch of clothes. So then you have this subset learning and everything. UK retail is also like another retail set, and this movie lens is a movie recommender data set. And for the algorithms which we looked at for online to neighbor, online local search with stash, online greedy, and this offline is a K-pass algorithm. So you have these things which are better. Here the key. So this is more of like these are empirical results. So your algorithms give better quality, and there is some trade-off between the space and solution quality. If that local search algorithms, you have some parameter which dictates how many times you want to do that swaps. And if you're allowing more space, then you can get more better solutions. We'll not discuss this hard instance with lack of time. So some future directions for this work, the guarantees which we had were only for the streaming setting. For the online algorithms, we could not prove any approximation bounds. So the question is, so we had this hard instance, right? So that hard instance shows that you basically cannot do better. So that hard instance, actually, if I go to it, yeah. So this hard instance, what we showed is that for that particular instance, all of our online algorithms, they output a 0 objective value solution, whereas the optimal solution has a non-zero value. So it's giving you like an infinite gap. But in practice, the things which you look at are not actually hard instances. So essentially, if you know about the simplex algorithm for LPs, then the hard instance there is taking exponential time on some very particular polytope, Kleemann cube or something. But in practice, you never actually, you rarely encounter that particular polytope. So similarly here, we do have an artificial hard instance, but the data sets don't actually translate to that. So can you prove better bounds for our online algorithms under some assumptions on the data, essentially to go beyond worst case analysis, and also designing new streaming and online algorithms for this problem using ideas from algorithm for submodular function maximization. I did not go into the proof details, but essentially like all of these greedy algorithms are very related to the submodular function maximization greedy algorithms. And this problem is not like the objective function is not exactly submodular, but it's something which is called close to submodular. So there is some parameter, and if you show some approximation factor in the submodular setting, then with some loss, you can translate it to this close to submodular setting. So you can essentially translate a lot of the streaming algorithms for submodular function results here with some loss in parameters. Some of them also break. So can we design new algorithms? And the particular algorithms we give are all like single pass algorithms, but you can design algorithms with constant number of passes, more than one, but less than k. And that ends that section of the talk and also the talk. If you have any questions, please feel free to ask.